Hi guys, welcome to this video of materials phenomena, this video series of materials phenomena in nuclear environments. So in our last video, we've discussed the environment of a light water reactor, and we've also discussed why we need such high pressures in a light water reactor. We've also discussed that our material for the reactor needs to withstand high pressure, high temperature, the radiation of all sorts, for example the neutron radiation, and of course just a reminder, we don't just have neutron radiation. In any radioactive material we'll have alpha radiation, beta radiation, and gamma radiation. So you'll need the material to withstand all these kinds of radiation damage, and of course resist corrosion. So what happens when at the atomic level when all this radiation actually hits the material? Now to start, we want to discuss neutron radiation because that's one of the primary things that actually happens in the reactor. We have a lot of neutrons going on, or a high neutron flux. So we have a lot of neutrons flying around in the reactor and hitting the atoms. So we have like neutrons, very small neutrons here. They're flying around, hitting the atoms, they're bouncing all over the place. So what happens at the atomic level when neutron radiation so-called hits the material? For this, we need some prerequisite understanding. We'll need to know what a crystal structure is. So these are some of the basic knowledge that you need to know. And of course, I'll try to put some of the links inside the description in order that you might understand this video. So talk about crystal structure, crystal geometry, what a unit cell is, what a lattice is, what is a defect, crystal defect, what is a vacancy, and what's an interstitial, and what are dislocations. So you have the standard types of edge, you have a screw, you have mixed dislocations, and of course how these dislocations move. And these are basically via slip planes. Okay. You also need to know what vectors actually describe a dislocation. So these are probably what you'll need to know, at least on a conceptual level, in order to understand what a neutron does to a material at the atomic level. So if you're not familiar with the terms I've just described here, please do watch the videos. So yeah, I'm going to assume you already have this knowledge, so we'll just continue on. So at the atomic level, we know that we have crystals. We have crystals made of atoms arranged in a very orderly manner. And two of the most common structures in metals that we use for the nuclear reactor pressure vessel, which was talked about before. Remember, we had this big containment that we need to hold all that pressure in, the pressurized water in, and prevent the radioactive material from leaking out. We have two very common crystal structure types. First is the body-centered cubic. So you have, let's say, a lattice cell here with one atom at each corner, and then one atom in the center right here. Okay, the picture is not that clear, but let me draw it in a very, maybe not draw the atoms being such a big circle, so that draw smaller atoms so that you can see where they are actually. So one at each corner. And one at the center. That's a body-centered cubic. You also have face-centered cubic. So again, in each lattice cell, so yeah, one at each corner of the cube and one on each face. So there'll be 6 faces: the top, the bottom, the left, the right, the front, and the back. So all in all, the idea is that we will have materials or having their atoms ordered in a very orderly fashion in a crystal lattice. So yeah, so let's just represent the lattice like, we have this kind of atoms like this. So we have a neutron coming in. You have a neutron coming in, and then let's say it hits the atom. Now what can it do? So a neutron comes in. There are 2 main things that can happen. First, you have a transmutation. So what happens is this: the neutron actually fuses with the atom. The neutron fuses with the atom. So let's say you have this atom and a neutron here, and then once it fuses with the atom, it fuses with the nucleus. This nucleus will be in an excited state, and gamma radiation can be released. Or in some instances, when the neutron is very energetic, let's say you have a nucleus here. So you have protons and neutrons in there. So ... and etc. We'll have lots of protons and neutrons. So you have a neutrons which are okay. Let's make it consistent. Neutrons, that is you'll make it a white circle. If you have a neutron coming in at such high kinetic energy, sometimes it can knock a proton out. So these are known as NP reactions. Sometimes it can knock an alpha particle out. This is called an N-alpha reaction. An alpha particle is just a helium nucleus. Sometimes the neutron can just fuse with the atom if the energy is pretty low. It can just fuse with the atom, and it fuses with the nucleus, and then it leaves the nucleus at an excited state, and it releases gamma radiation. So this is known as an N-gamma reaction. In all these instances, the original nucleus has changed its identity from one element into another element. For example, if a neutron fuses with copper, let's say copper 63, it becomes copper 64, and this is excited, so I just put a star there. So it will undergo gamma decay and release gamma radiation. So this nucleus is in an excited state, much like how, if you pump photons into the electrons of the atom, the electrons themselves will be excited, and the atom is said to be in an excited state. So similarly, when the neutron fuses with the nucleus, the bond between the neutron and the nucleus is very strong, so that releases a lot of energy, and that excites the nucleus into an excited state, and the nucleus will de-excite itself by releasing photons. In this case, it's gamma radiation. Now this copper 64 is also unstable, and it will release in sometimes what is known as a beta decay. And basically it can either release an electron or an anti-electron, which is also called a positron, and it can either decay into zinc 64 or nickel 64 in order to become more stable. So you can see that in a transmutation reaction, a number of particles can come out. So you can have gamma particles coming out, or gamma rays coming out. You can have alphas coming out. You can have protons coming out. You can have different elements being formed. Then you can have electrons and anti-electrons coming out, or positrons coming out. And these positrons tend to end up annihilating with electrons. So these positrons will eliminate an electron, annihilate an electron, and produce two gamma rays of 511 keV. So that is the E equals mc squared, where the mass of the electron is converted into the energy of the gamma ray. So this is known as nuclear transmutation. And for some elements, this happens to be quite a problem, especially with copper. With copper, this tends to be a problem. So, and every time a nuclear transmutation happens, it can create all these unwanted particles that can cause even more radiation damage to our material. So for our nuclear reactor made of steel, or nuclear reactor pressure vessel, called RPV, we have it made of steel. We need to make sure elements like copper, or these isotopes like copper-63, they should be in very low concentrations so that you have less of this transmutation happening. If not, you have all these unwanted particles that will be lodged inside the metal. For example, you have lots of the beta rays, or you have lots of zinc and nickel being formed, and then that can change the properties of the steel, like the yield strength and all that kind of stuff. And it can make it more brittle, and that's what you do not want. So we need controls on elements like these. So preferably when you talk about reactor pressure vessels, you have to control these kinds of elements. So that's one aspect of neutron damage, which is transmutation. Now the other one, which is kind of more straightforward, is basically the neutron will transfer some of its kinetic energy into the nucleus. Okay, not the atom. Because you see, when you talk about atoms here, we might think of them as, being hard spheres. But we know from Rutherford's experiments, well, the atom is made of an electron cloud and a very small nucleus. So the neutron, being electrically neutral, it doesn't interact with the electron cloud here. It will only interact with the atom by hitting the nucleus itself. So the neutron must hit the nucleus in order for it to transfer its kinetic energy. So let's take a look at that. How much energy is being transferred, and how much is enough to dislodge this atom? Is the energy so much that it will just knock the atom off? Well, if it exceeds a certain threshold, the kinetic energy transferred to this nucleus is enough to knock this whole atom off. And that's what we want to explore in more detail. So how much is that threshold energy usually? Well, for an iron atom, we are talking about 25 to 35 electron volts. So let's use this as an example. We just take the energy threshold, 35 electron volts per atom, to approximate the energy needed to dislodge or displace an atom. So we call this the displacement energy. And this is what I will call ED, energy of displacement. Alright, so if the neutron transfers enough kinetic energy, which is more than this atom will be dislodged or displaced. So for us to know how much energy is being transferred from the neutron to the nucleus, and this is usually an iron nucleus, iron 56 because that's what most of the steel is actually being made of. It's made of iron. It's an iron alloy. Okay, so when a neutron hits the iron, what happens? We have to come back to our basic conservation of momentum, and conservation of kinetic energy. This is a basic physics we should already know. So the law of conservation of momentum says that for any closed system, the combined momentum of the initial states. So let's draw this out. We have a neutron, neutron hitting onto a iron nucleus. So the neutron will just scatter at some angle, theta, and the neutron will scatter off at some angle theta, and this nucleus can scatter off at some angle phi. And depending on the angle that the nucleus is being scattered at, the amount of momentum and energy being transferred will differ. So all of this is based on the conservation of momentum and conservation of kinetic energy. So again, let's do this. Let's make it a bit clearer. The mass of the neutron times the mass of the velocity of the neutron at the initial state plus the mass of the iron times the velocity of the iron at the initial state equals to the mass of the neutron. So this is the momentum of the initial states, which is over here. So this is the initial momentum, and the final momentum should be also the same. Plus MFE VFE final. Okay. Another way of writing is also using the letter P to represent momentum, and that will be PNI plus PFEI. So this is momentum of the neutron initially and the momentum of the iron initially. That will equal to the momentum of the neutron at the final state plus the momentum of the iron at the final state. Okay, so these are our conservation of momentum equations right here. Okay, so what about kinetic energy? Well, we can do this half. So this is the initial kinetic energy of the neutron. Okay, so initial kinetic energy of the neutron and initial kinetic energy of the iron nucleus. And that will equal the final kinetic energy of the neutron and the iron nucleus. So solving this simultaneously will help us to determine what will happen to this iron nucleus. Okay? So the simpler way of writing kinetic energy, let me draw. The simpler way of writing this same law is representing all this by the letter T. That is often used for to represent kinetic energy of an atom or a nucleus or any kind of body at a subatomic level. Okay, so T represents kinetic energy. And I mean, you can also think of it as a temperature, because kinetic energy on a subatomic level, it does correlate very closely, or it's pretty much, its temperature. Okay? And what is the relation between the momentum and kinetic energy of a body? For any body, we know that the kinetic energy of any body is equals to p squared over 2m. This is a very useful relation we want to use. Okay? Now, with all this information, we want to consider two very simple cases. Now, what I said earlier is that as theta, the angle at which this neutron actually scatters off, as this angle changes, the amount of energy and momentum being transferred also differs. Now let's consider two very extreme cases. One is the theta equals to 0 degrees, and the other case is where theta equals 180 degrees. This is case 1, this is case 2. Now let's say theta equals to 0 degrees. So when theta equals to 0 degrees, the neutron actually just keeps traveling forward. And the iron atom should also, theoretically speaking, it may also go forward. So let's consider momentum in the x direction only. Of course, there's momentum in the y direction, but we'll see later why it doesn't really matter anyway. So at 0 degrees again. So P and I plus P F E I, P and F plus P F E F. So this is case 1, where theta equals to 0 degrees. We know that in any case, the initial momentum of the iron atom we assume to be 0, because we neglect any vibrational effects, and basically we neglect its temperature. Because the neutron is coming at such high kinetic energy, usually it's at 1 MeV for a nuclear fission reaction. The neutron's coming in at about 1 MeV. That's 1 million electron volts. And now the typical temperature in a nuclear reactor, it doesn't even exceed 100 electron volts of energy. So you can see that compared to this 1 MeV, whatever temperature this iron atom is having, it doesn't really matter at all. Okay? So the kinetic energy and the momentum of the iron atom initially is pretty much 0. So let's take a look at our second equation as well. It's T and F plus TFEF. Alright, so this will also equal to 0. Okay, so we'll have these two equations now. P and I, P and F, PFEF, this is the momentum in the x direction. And this is the kinetic energy equation. Now what do we actually want to find out? We're actually interested in finding out the final kinetic energy of this iron atom, or iron nucleus to be more precise. So this is what we want to find out. So let's make this a subject. Alright. Okay, so now we have this. Can we substitute terms in? As we said earlier, this is the initial kinetic energy of a neutron. Typically speaking, it's 1 MeV. What about this? How can we find the final kinetic energy of the neutron? Now basically we want to start substituting some of these equations in. Some of the momentum balances into this equation. How do we do so? we use this relation. So let's take this equation, put it here. We have the final kinetic energy of the neutron, and that will equals to the final momentum of the neutron squared divided by 2 times the mass of the neutron. Okay, so let's substitute that in. Okay, now that is substituted in, we want to find out what this is, what P and F is. If you're not sure, we can take a look at this. So P and F equals to P and I minus PFEF. So you just rearrange this equation. P and F equals to P and I minus PFEF. So that's the momentum of the neutron initially minus the momentum of the iron at the final state. So let's write that out. Okay, there you go. And we want to substitute that into this equation. All right. Okay, so yeah. We'll get this relation when we have, after substituting this equation in. So let's see what it turns out to be finally. T and I minus square minus 2 Okay, we will have an expression like this. Okay, so let's write all the stuff out. So minus times this will be the minus, the middle part will be a plus, and then this will be a minus. Okay, so that is PFEF squared over 2mn. Now what do we notice? Excuse me. Yeah, what do we notice? For starters, we notice that this T and I and this, they are exactly the same because of this equation, how kinetic energy is related to its momentum. You can see that actually these terms cancel out. Okay, so we are left with P and I, PFEF 2mn minus PFEF squared over 2mn. So it's still a bit messy, but we can continue to simplify this equation. So what's the next step? We'll have this, which is, we kind of know it, but this is relatively unknown. So we'll need to consolidate our unknown terms to one side, sort of. Okay, So how can we do that? Yeah, how can we do that? We may want to simplify our equation to make it look a bit neater, to make everything in terms of kinetic energy. Yep.